Hi all! This episode of Physical Attraction is brought to you by the American National Standards Institute. Standards make the world go round, and they also dictate what is round. Without standardised measurements and definitions, physicists would be speaking to each other in different languages and would struggle to understand the universe even more than we already do. You can learn about standards in America at the ANSI blog at blog.ansi.org/pod to learn about how standards apply to you. Now on with the show.
Into his eyes. They're the eyes of a man.
Hello and welcome to Physical Attraction. We are, and remain, the only show out there that's going to explain to you physics, one chat-up line at a time. Today we'll be continuing our look at the life and career of Isaac Newton, a man who needed no help with physics, but some serious help with flirting. Or possibly he had no idea to chat anyone up at all, which is just fine by the way. At one point he fell out with his good friend John Locke, and mid-nervous breakdown he hid himself away from everybody. When he wrote a letter to Locke to explain himself, he apologised, saying, quote, "Being of the opinion that you endeavoured to embroil me with women and by other means, I was so much affected with it, as that when one told me that you were sickly and would not live, I answered 'twere better if you were dead.'" Wishing death upon your friends for attempting to, quote, "embroil you with women," when you're in your mid-50s, might seem a little bit extreme, but I guess if anyone's ever been on a blind date that their friend set up, they might just sympathise. But we are not Newton, so this episode's chat-up line is a gravitational one. I like those clothes. They look better accelerating towards my floor at 9.8 meters per second. For that is the universal rate of gravitational acceleration on Earth's surface that all objects have. Of course, this would only be the acceleration rate initially, before air resistance comes into play, but apparently when someone throws their clothes to the floor in a fit of passion, whipping out a portable whiteboard and attempting to calculate the drag coefficient, quote-unquote, kills the mood. I mean, if anything, it just enhances it, but if that's your opinion, sorry. So when we left off in our biographical history, Newton had just left Cambridge due to the plague after a successful but undistinguished undergraduate degree, and he's now holed up in his house in Lincolnshire. It was here, in a diary inherited from his stepfather that had plenty of blank paper, he began his calculations in a book that's now called the Waste Book. Essentially, the most important part of what Newton was working on here was the fundamentals of calculus. Now I have to point out that Leibniz also developed the calculus alongside Newton. There's a huge controversy about this that started when both men were alive, and essentially has continued to the present day without ever being properly resolved. So the real question is, did Newton develop calculus and did Leibniz copy him, or vice versa? And I think really the most likely explanation, and the one that historians have settled on, is that they both came to it independently. After all, mathematics is really discovered rather than invented, and this is especially true of calculus that governs so much of the world around us. There's some evidence that Leibniz saw some of Newton's papers while he was working on calculus. It's also fair to say that Newton didn't publish his calculus in full until well after he claimed to have finished it. The two even worked together on some aspects of the mathematics. So for convenience's sake, because we're talking about Newton, I'm going to talk about it from now on in terms of Newton's life, but just remember the caveat that he probably wasn't the only one who discovered it, and he certainly wasn't the only one who could have discovered it. Nevertheless, it was still a huge achievement. Fine. So what is calculus? Well, it's essentially the mathematical study of change. Before calculus, we had geometry. Now that's the study of relationships between things like areas, volumes, distances, shapes in 2 and 3 dimensions and more, that kind of thing. And here you have theorems like Pythagoras' theorem, which relates the lengths on a right-angled triangle, and so on. And you also have algebra. So algebra is the study of calculating things where the numbers you're calculating with are completely general. So for example, the square of a number is a number multiplied by itself. We have squares. 1 squared is 1, 2 squared is 4, and so on. But the operation to square a number is an instruction on what to do with a number, multiply it by itself. And algebraic equations are instructions applied to general numbers, any number you like. So saying x squared is the same as saying whatever x is, square it. And that way your calculations are completely general, you plug in the numbers at the end, and you can figure out how things will be expressed in terms of that original input variable x. So geometry studies shapes, areas, volumes. Algebra studies rules, operations between numbers. Calculus studies changes, and it turns out you can get to all kinds of rules and useful results by considering infinitesimal changes. Changes that can be as small as you can possibly think of. So to see why, I think it's helpful to imagine calculus in this sort of sense. Imagine you've got a graph, a line. You can make it as wiggly or as straight as you like, as long as it's continuous. There are no gaps in the line. If you zoom in on a segment of that line far enough, eventually it will be approximately a straight line, the bit that you're zooming in on. Because the change that you're considering, the section of line that you're considering, is infinitesimal, you can always zoom in far enough that the line is approximately straight where you're looking. And then you can say, if I'm at this point and I move infinitesimally along the line, this is the direction I'm going in, along that straight line. So you can imagine it in terms of a hill, which would be the function y equals minus x squared, for example, forms a nice hill. When you're at the top of that hill, the very, very top, and you move a tiny distance, what you're actually doing is moving horizontally. You don't move up or down the hill, really, because you're still incredibly close to the top. So you're moving in a straight line, even though, in fact, the curve that you're on is curved. So the direction of that straight line is like a rate of change. It's like looking at a stock exchange graph and saying, okay, at precisely 12 noon, how quickly was the price changing? If I wait a small second, how much will it go up or down? Finding the rate of change of something, how quickly something changes, that's differential calculus. Similarly with our hill example, there'll be some point during the ascent of the hill where it's the steepest, and at that point the rate of change of height with distance is the most. That's what it means to say the hill is steep. When you move a certain distance along the hill, your height is changing by the maximum possible extent. So similarly in our stock market again, if you have the rates of change of your stock price at all times, you can work out how much it's changed overall. You can go from the gradients, from the rates of change, to the value of the function itself. And it's fairly easy to see how you do this, right? You just say, okay, if it changed by 5 points per minute 10 minutes ago, and it stayed like that for a minute, then that little minute it must have changed by 5. And you carry on going like that, you add them all up, and you go from the gradients, from the rates of change, to the value of the function itself. So this is the reverse of differential calculus. From how something changes, you determine what it must be now. And this is integral calculus. So the importance of this really can't be overstated. Pretty much anything that deals with anything changing is going to require calculus to deal with. And since the job of physics is absolutely to make predictions about the future, we need to understand how things change with time. And it turns out there are all kinds of useful relationships. If you differentiate distance travelled, you get velocity, the rate of change of distance. And if you differentiate velocity, you get acceleration. That's how quickly your velocity is changing. So if you want to know things like how quickly something's moving, where it will be, how fast it's accelerating, you need to express it all in terms of calculus. Similarly, in general, you can integrate the velocity to get the distance that's been travelled, and you can integrate the acceleration to get the velocity that you have. So we're familiar by saying, okay, distance is speed multiplied by time. But obviously that only works if the speed is constant. If the speed is changing over time, then you have a more difficult function to deal with. So what happens if the speed is changing? Well, then you can say that the speed is approximately constant as long as the time period that you're talking about is very, very small. Small enough that the speed hasn't had time to change. And then what you're looking at is adding up lots and lots of tiny time periods where the speed is approximately constant, and then the distance covered in each of those tiny time periods using the formula distance is speed times time. And it turns out that that sum can be expressed in terms of an integral, which is very similar to a sum. And what Newton discovered is that you could get to old mathematical results, things that people knew to be true already, by using this calculus. By adding together lots and lots of infinitesimal disks, for example. Again, this idea of an integral being like a sum. You can calculate the area of a circle. By adding together lots and lots of infinitesimal shells, you can calculate the volume of a sphere. So you could use calculus to get lots of the old results of geometry and algebra, and to prove lots of things that had previously only been observed or had been discovered but never proved. So now suddenly you had a way of instantly proving the formulae for the volume of a sphere or a cone, anything you like. Now this mathematics was so new when Newton published things that he discovered using calculus, he basically had to express it all in terms of geometry, which was considered to be proper mathematics. And he derived every result in his work very, very carefully, with completely flawless logic, step by step, from a series of statements that no one could possibly disagree with. So in mathematics, these statements, which kind of define the math you're using, the logic of the world you're in, they're called axioms. And the ideal proof derives everything from a set of basic axioms. So his habit of doing this, doing things very, very carefully, very, very methodically, meant that it was actually Leibniz who developed the convenient algebraic notation for calculus that mathematicians and physicists know today. And this style also means that the Principia Mathematica, Newton's most famous work, is pretty much unreadable for the modern author. In fact, when I was applying for undergrad, I originally wrote on my personal statement that I'd read the Principia and been inspired by it. Then I accidentally sat down and tried to read the Principia. A few hours later, I sheepishly removed the reference to the damn thing from the statement. There was no way I was going to read it. It is dense. And it shows you something important. A lot of what Newton discovered that seems completely obvious to many of us now, it was not obvious when it was discovered. It took a very long time and a great deal of complexity to figure these things out. In the last few hundred years, we've digested it and condensed it down to a form where you can learn about it in school or university, and I can try my best to explain it to you over a podcast. But initially, this stuff was cutting-edge, highly technical mathematics. And for the mathematically minded out there, it's going to seem very simple to say that the derivative of x is 1, or that the derivative of x squared is 2 times x. But if I asked many of you to prove that, without reference to Taylor series, without reference to derivatives, without reference to small changes in functions and so on algebraically, if I asked you to prove it to me using only the theorems of geometry, well, you might find it difficult to get lots of the results of calculus that we now take for granted. So I don't think it's worth saying that Newton did things in a particularly obscure way because he had some perverse liking for things that were obscure. It's just that this was the only way he could demonstrate his revolutionary new mathematics was true. Amongst other things, he did work in infinite series. So it turns out that you can approximate many functions in mathematics, like the sine and cosine trigonometric functions that deal with ratios in triangles, and also express the mathematics of waves, or the exponential function that we've talked about in our Teotwalki episodes that you get when something's doubling. You can express lots of these functions by adding together lots of algebraic expressions. So for example, instead of the exponential function of x, you can have 1 plus x squared over 2 plus x cubed over 6 plus ... and so on. And it's crazy mathematics really, because to get to the true value for e to the x, you technically need to add together an infinite number of terms. But under certain circumstances, the higher order terms are small and you can ignore them. In this way, more complicated functions can be converted into powers, squares and cubes, which are mathematically easier to deal with. After all, you know how to evaluate a square, or a cube, or even something to the power 4, when you put in a number, but it's not immediately apparent how to evaluate sine of x when you put in a number. Most people will do it in terms of a calculator or with reference to some lookup table, but it's not immediately apparent how you can do it. This method is sometimes called Taylor expansion, and it's basically all of physics. Okay, that's a slight exaggeration. It's most of physics that doesn't need computers to solve. But seriously though, anyone who's studied a physics degree will agree with me. Taylor expansion is a huge deal. Without the stuff that Newton was working on, we'd all be completely stuffed. This development of calculus was really a lifelong work. It took decades to fully exploit it all. But the fact he was able to prove old results in a more efficient and elegant way than before drew people's attention. By 1669 he was being described in letters as, quote, Mr. Newton, a fellow of our college and very young, but of an extraordinary genius and proficiency in these things. Newton was soon appointed as Lucasian Professor at Cambridge and a Fellow of the Royal Society, which both remain incredibly high honours in the field of science. But he didn't initially lecture about calculus. He was more concerned about optics. What Newton essentially had discovered that had him so excited was that simple white light was not so simple after all. All the way back to Aristotle, people had thought that light was naturally white, and the colours basically arose from mixing light and dark in certain ratios. Obviously this wasn't going to do. Newton noticed something called chromatic aberration while looking through his telescope lenses. We know now, as he discovered, that this pattern of colours is caused because of something very fundamental. The way that light refracts or bends in glass. It depends on the wavelength of the light. And since different colours of light have different wavelengths, they were bending by different amounts. This means that with a simple experiment, one that you probably did in school, Newton could use a glass prism to split light into all the colours of the rainbow. The colours weren't really a mix of light and dark at all. Instead, somehow, bizarrely, white light was a mix of all the colours. When water droplets do this in the air, we get a rainbow. By analysing the strange, new, colourful light he was producing, Newton came to a few interesting conclusions. Again, you have to remember the time that we're living in. Newton has no idea that this is because light is a wave with lots of different wavelengths. Newton has no idea what's going on with light. But he is trying to understand how it may behave by looking at the properties of what it does. So first he noticed that no matter whether the new light was refracted, reflected, whatever, it didn't change colour. It seemed that the colour was an intrinsic property of the light. In Newton's own words, quote, I might add more instances of this nature, but I shall conclude this general one, that the colours of all the natural bodies have no origin other than this, than that they are variously qualified to reflect one sort of light in greater plenty than another. In other words, he figured out that the objects aren't so much generating the colour themselves. Instead, they're interacting with the light that already has various colours, and some intrinsic property of the object determines what colour it is, because of what type of light it reflects. But Newton, in his theory of light, was starting to touch on a real physical controversy. He didn't know it yet, but part of what he was thinking about would lead to controversies that would need quantum mechanics to solve. Newton was already trying to think about the nature of what light was fundamentally, and he felt convinced that it must be corpuscular, or made up of little particles. In Newton's view, this explained how light could be refracted or bent when it goes into a different substance. So we see this light is refracted in water and in glass too. The little particles of light, in Newton's view, bounced more when they travelled into a denser medium. This, for Newton, explained why glass bent light more than water, and why water bent light more than air. Because it moves into a denser medium, and the little particles are colliding more often. Newton felt that light should be like particles and not like waves. This is a belief that Newton had throughout his life, really, even back to his school days when he was writing questions concerning natural philosophy. He said, if light was a wave, as people like Huygens were suggesting, surely it would bend around corners, like sound waves do. Instead it seemed to travel in straight lines. It could be blocked by objects, casting shadows. Particles travelled in straight lines, so light must be a particle. The world probably wasn't ready for our modern theory on light, which has ended up being a rather strange mix. Particles that sometimes behave like waves, waves that sometimes behave like particles. So it's perhaps fair enough that Newton didn't get everything right on light. But it's worth saying that because of how well respected Newton was, his corpuscular theory of light dominated for more than 100 years, even though it couldn't explain aspects of light that Huygens' theory could. And I think the fact that he never changed his mind on this, despite the evidence, maybe you can begin to hold against him. And in his corpuscular theory on light, we begin to see some of the dark sides of the character of Newton, because whatever else he was a highly sensitive egotist who couldn't stand for any criticism at all. Remember last episode when we talked about his feud with Hooke? This is probably where that feud began. To quote from St Andrews University, in 1672, Newton was elected a Fellow of the Royal Society after donating a reflecting telescope. Also in 1762, Newton published his first scientific paper on light and colour in the Philosophical Transactions of the Royal Society. The paper was generally well received, but Hooke and Huygens objected to Newton's attempts to prove, by experiment alone, that light consists of the motion of small particles rather than waves. The reception that his publication received did nothing to improve Newton's attitude to making his results known to the world. He was always pulled in two directions. There was something in his nature which wanted fame and recognition, yet another side of him feared criticism, and the easiest way to avoid being criticised was to publish nothing. Certainly one could say that his reaction to criticism was irrational, and certainly his aim to humiliate Hooke in public because of his opinions was abnormal. Indeed, he wouldn't even publish his major work on optics, which was called Optics, with a K, until after Hooke died. Even then, to explain some of his observations on optics, Newton needed to appeal to some of the wave-like theories of other physicists. But Newton didn't like these wave-like theories, because they posed a confusing question for the physicists of the day. If light is a wave, then what's waving? Huygens, who was in favour of the wave-like approach to the description of light, had posed the idea that there was something called the luminiferous ether, some invisible substance that filled the universe and vibrated to transmit the waves of light, in a similar way to the way that matter vibrates to transmit waves of sound. But Newton hated this idea. In his view, if the universe was full of luminiferous ether, surely they'd be able to see how it interacted with matter. He said that, in terms of the ether, it would disturb and retard the motions of those great bodies, the planets and the comets, and thus, as light's medium is of no use and hinders the operation of nature and makes her languish, so there is no evidence for its existence, and therefore it ought to be rejected. But then when Newton wanted to explain how heat could propagate through a vacuum, as it does, he needed to invoke some kind of ether to make sense of his results. He didn't realise, as we now do, that both light and heat can be delivered by electromagnetic radiation, which doesn't require any ether to hold it. Newton may have rejected a universe filled with a wavy ether that transmitted light, but he couldn't demonstrate that his corpuscles were real either. He couldn't explain why they didn't explain everything about light. The problem of light and its true nature probably troubled Newton for all of his life, and it would trouble physics for hundreds of years to come. It would be wonderful to jump in a time machine and tell Newton about our modern theory of light, and see his reaction. Maybe he would have hated it, or maybe as soon as it was explained it would have all made sense to him. I think that quantum mechanics might not have upset him all that much, though. He might view it as an aspect of the occult. But at the same time, he was almost groping after some wilder truths. In Newton's mind, light was made of very fine particles, so small that it was impossible to see them, while matter, physical things, were made of heavier, bigger corpuscles, bigger particles. But fundamentally they were the same thing, he thought. So in Optics he wrote, quote, "Are not gross bodies and light convertible into one another? And may not bodies receive much of their activity from the particles of light which enter their composition?" When Newton saw light, he imagined tiny grains of sand streaming at incredible speed from candles or lamps or the sun, crashing into things and being reflected or refracted, and he imagined that if these tiny grains of sand might flow into bigger grains of sand and change them, and perhaps if you were clever enough and went through the proper procedure, you could turn light into matter. And we now know, of course, that in some ways Newton was right about this. Matter, what Newton called the gross bodies, which is not a good Chatterline, by the way, matter is really just a form of energy, and in fact matter and light can be converted into each other. When matter and antimatter collide, you get photons of light, and photons, in turn, can produce matter and antimatter. So in some ways Newton was hundreds of years ahead of his time in this observation. But we have to remember that he obviously wasn't thinking about matter and light in terms of energy. He was thinking more of a sort of alchemy, some kind of process that could be found which, when applied to light, might somehow compress it or transform it into matter. And see, this is one of the things about reading Newton's earlier works. People often pick out individual sentences to say, Newton predicted quantum mechanics, or Newton predicted special relativity, or Newton understood more about matter and light and energy than he really did. The reality is that he said a lot of things, and a lot of them were quite vague, and I think that if all of the things he said that were dramatically incorrect had made it through history and were widely shown and touted and so on, we probably wouldn't view him as prescient as some people have tried to make him out to be. But that doesn't make his genius any less dramatic. You have to remember that nowadays it's so easy for us because we're building on so much science that has gone before. But in the case of Newton, there really wasn't too much to go on. It's a time when people are still burning witches. What's so important to remember about Newton, though, was that in many ways he wasn't altogether a physicist. He wrote more about alchemy, transforming substances into each other, than he wrote about physics. Modern physicists have the established scientific method. It's been used for centuries. We have rationality and we have experiment, and we have robust theories to explain most of what we see around us in the world, to build upon. Newton had his experiments, he had his senses, he had his judgment, but also he had an innate sense of how he felt the world should be. And that was informed not only by what he saw in the world, but by centuries of superstition and law, much of which was terribly wrong. His ideas, as we've seen, were often his own and flew in the face of consensus. But you have to remember that he lived in a slightly more magical age than we do today. The point here is not that Newton was irrational or crazy or stupid. It's that the realm of things it's reasonable to investigate in science changes over time. We know that he sought out reasons, order, explanations. It's just that sometimes he thought the explanations were beyond human understanding, which was true of many things in the 1700s. Many things were beyond human understanding, and it's still more true than we'd like to admit today. And one thing that's really fascinating is that you can make a good argument that Newton's belief in alchemy, in occult and the supernatural, and things that didn't quite fit with the rationality of men like Descartes and others who had come before him. You can make a good argument that this belief in magic was part of what allowed him to make the intellectual leap to come up with a theory of gravity, which will be the subject of our next episode. Next time we'll deal with Newton's laws and how they laid the stage for all of classical mechanics. We'll talk about what's actually in the Principia and how Newton worked out the motions of the heavens. And of course we'll get around to that time he nearly had his brain smashed in by a rogue, anti-science apple. Thank you for listening to this episode of Physical Attraction. If you enjoyed it, please tell as many people as you possibly can about the show. If you tell one person, and if every listener just tells one person to listen, then after 30 or so episodes, we'll have over 1 trillion listeners. And I think that would be a really good achievement. You can engage with us on Facebook. We have both a Facebook page, Physical Attraction, and a discussion group that goes on there. On Twitter, we're at PhysicsPod. I post stuff there all the time, more than I probably should. Also on the Twitter, you'll see that you can donate to the show if you're interested via the PayPal link. You can like us on Facebook, you can review us on iTunes, you can favourite us on iTunes. All of that helps get word out about the show. Alongside this, I want to say that you can visit the website at www.physicspodcast.com, and if you comment on the episodes with your listener questions, they will all feed into a listener questions episode at some point in the future. I want the show to be a dialogue between me and you, so if there's something I've said that's wrong, if there's something I've said that you're interested in, if there's something you've always wanted to know about physics or anything in general, just ask and it will go into a future episode. You can determine the topics of this show just as much as me, so I think that's quite a good way to democratise things between us. I'll see you next time. Until then, don't embroil yourselves with anyone, unless you enjoy it.